So thank you. My name is Andreas René Geist. I'm a postdoc with Georg Martius in the Autonomous Learning Group of the University of Tübingen. And today we talk about our work on SoftJAX and SoftTorch. So what is the problem? Well, assume you have a machine learning framework, for example, a neural network, and you want to send the output of your neural network through a discrete operation such as rank. So this is what you see here, this step function, where if you now would compute the gradient of this function using automatic differentiation, the gradient is 0 everywhere, and you can't do gradient-based optimization. What you want is a smooth approximation of rank, which if you take the naive approach, if you take the naive approach, you would now look essentially for soft operators, smooth operators that approximate the rank function. Then you would read the papers, would think about, okay, which one is the best of the recent methods that have been presented, look at the GitHub repository, port the code to your code project, and then get running. If you have a project where you have a lot of different discrete operations, then it's actually quite a lot of work to combine them, put all these frameworks together. And this motivated us to take this existing literature on soft operators, and instead of all of it being spread out across repos, put it into one repo. And this is either SoftJAX if you're using JAX, or SoftTorch when you're using Torch. And so, for example, this function here, you have an array with different entries. Your first entry we call x, we can vary it, we give it to the rank function, and what we would like is a soft approximation. In SoftJAX, what you do is you pip install the SoftJAX library, you replace the JAX rank operator with SoftJAX rank. And then optionally, you can decide on a method you want to use, which algorithm, and then what kind of regularization or projection mode. In this case, for example, here, the smooth projection. And so SoftJAX doesn't do this only for rank. We try to make it as feature complete as possible. So there are a lot of different operations that work on axis, that work so on a complete axis of an array, such as sort or quantile. There are operations that work on individual elements of an array, such as round. Logical operations that compare elements of an array, and of course, selections. So what is softening? The perhaps canonical example for softening of a function is the ReLU function. So for negative values of the input to the ReLU is actually 0, so you get dying gradients. And what you could do is replace your ReLU function with the soft plus. And then use the gradient of the soft plus. The advantage is you have smooth gradients, but in some cases, you actually don't want to replace the ReLU in your forward computation, because you might want to have sparsity in due to the ReLU. And so what you can do is what's called the straight-through trick or straight-through estimation. You take the hard function, in this case here the ReLU, wrap it in a stop gradient operator. Then you add the soft function, here the soft plus, and directly subtract the soft function again, wrapped in a stop gradient operator. And so your automatic differentiation library, when you now do backwards mode autodiff, uses now the hard function in the forward pass, but if it needs to compute the gradient of the function for the automatic differentiation pipeline, it uses the soft plus. We also in the paper explain the straight-through pitfall, which is essentially, assume you now want to have you have two ReLUs that where both of which you want to use the soft plus for gradient computation. So you wrap each ReLU in this straight-through estimation trick. But now if you multiply them together, you due to the product rule in the forward pass, you still use for the function evaluation the hard function. And you see it here in this plot. So this is essentially X is the input to the first ReLU, Y is the input to the second ReLU. This is the product of two hard ReLUs. It's the gradient is 0 everywhere except for x and y positive 0. This is if you would just wrap the straight through trick around each function, then multiply them and let auto handle the gradient computation, then you still get a 0 area. And what we suggest in the paper is that you essentially do the product computation, but you apply the straight through trick on the outside of the function. I won't go too much into detail, but you see that you then have the gradients that you actually want. But a straight through estimation is just optional. It's just a feature. The really interesting thing is how do you get these soft approximations? For element-wise operators, it's pretty simple. It all starts with the sigmoid. So the Heaviside function, which can be, it's essentially a step function here in red. And you can approximate it with the sigmoidal function. So the classic sigmoidal function is the sigmoid, but you could also use a linear approximation. We also implemented different cubic polynomial interpolations. And depending on what kind of type you choose, you would switch between these sigmoidal approximations. Given the sigmoids, you can now define the sine, round, absolute, and clip function. I'm pretty sure most of you have done this in a project. The advantage of having it in one library is that you can just use it. You don't need to think about how was this again, especially for more complex functions such as round. It's actually not so trivial to implement it neatly. So given sigmoids, we can go one step further. We can look at comparison operators. And here we interpret the sigmoid just as a cumulative distribution function that defines the probability that this Boolean operator equates to true. So for example, here in the greater function, we have a value x that is compared to a value y. And if x is smaller y, then the probability that greater xy equates to true goes to 0. If you have these probabilities, then a classic way of smoothing discrete logic is fuzzy logic. So what you now do is you take these probabilities and you just compute logic operators as the computation of probabilities. So the all operator is just the joint probability of several probability events. The not operator is negating a probability. Given these two, you can derive any AND or XOR. And if you want to compute a value under two different probabilities, so pi is governed by xi and yi by 1 minus pi I, you essentially just compute an expectation. So this selection operator between two element-wise array values becomes an expectation. Here's an example for how XOR looks like. So now this discrete logic operator is now a smooth function. And of course, you could apply straight-through estimation on top to have the discrete logic in the forward pass and the smooth gradients in the backward pass. Really interesting, it actually gets when you go to access-wise operators. So what is the canonical example for an access-wise operator? Argmax. So assume here you have an array X. You want the maximum value. Argmax returns you an index. In this case, the maximum is at index 2. And then you can select the array entry by just selecting exactly the value at index 2. The important part is you select an Argmax outputs an index, and the selection returns you a value at this index. With SoftJAX, it's a bit different. So if you call now, if you replace JAX NumPy argmax with SoftJAX argmax, you now compute a probability distribution over indices. So the default mode of argmax is just the classical softmax function. So this is maybe not too surprising. But we also have it for different types, like if you specifically want C2 continuity instead of a smooth approximation. And selection now, if you have this probability distribution of indices, reduces to the computation of an expectation, an expected value at this index, which is nothing else than multiplying these probabilities with these array entries. So just computing the dot product between the two vectors. To just give you an idea about how a soft approximation of an of an access-wise operation could look like. I show you soft sort, not because it's the best method, but I think it's a quite simple method and gives you an idea about how soft approximations could work. So assume you have here an array with different entries. And you have now, the first thing you do in soft sort is you compute an anchor. And this is just applying the hard operation, the sort operator, on this array. So you get now the sorted array. The second thing is now that you compute between the array entries and the sorted array pairwise distances. So you get this matrix of pairwise distances. Then you take one row of the pairwise distances and you apply an access-wise unit simplex projection. So essentially, for example, you would apply SoftMAX. In turn, what you get is a probability distribution over indices. So what is the probability of each of these array elements to be the first entry in the sorted array? This already would be the output of argsort. So the output of argsort in SoftJAX is essentially a row stochastic matrix. And if you now want the output of sort, you would again just compute an expectation. So you multiply the rows, the probability distributions with the array entries, and you get the expected value for the first entry, and so on. Okay, but we didn't only implement soft sort. We tried to move the whole project towards being feature complete. So having many algorithms that you can actually compare to and decide which one is best for you. The perhaps, let's say, purest method is regularized optimal transport. We implemented as a baseline. Then I already talked about soft sort. Neural sort is very similar to soft sort. It computes a slightly more complicated anchor, but it also has quite nice smoothness properties. And then we implemented more exotic functions or algorithms, such as fast soft sort, which avoids the computation of a row stochastic matrix, but directly does the permuta-hedron projection into the space of sorted array elements. So it avoids this computation of so you don't get an output like argsort, but you directly go to sort. And sorting networks, which is also quite interesting, you essentially implement the sorting operation as a neural network. So you put in your array, the outputs get shifted around, and the output is then your sorted array. And right now, we are currently implementing LabSum. And of course, if you have an algorithm that you think would fit well into SoftJAX or SoftTorch, then please feel free to contribute. Like, the goal in the end is that we have a joint project. Let's quickly talk about how do these compare. So far, we didn't find that there's one vastly superior algorithm. Here we look at the computation time and the memory used for the sort operator. And what we see is that sorting networks are actually pretty fast, use like medium memory. And then if you're really interested in saving memory, fast soft sort, which avoids the computation of this row stochastic matrix, is actually really good on memory. Also, you see that for smaller array sizes, soft sort and neural sort are actually pretty fast. Lastly, let's look at a case study. What can you do with SoftJAX that you couldn't do before? And so our initial motivation was actually to smoothen collision detection in robot simulation, so a differentiable robot simulation. Here, Mutluko XLA or MJX. And what you see here is an algorithm that, given ordered polygon, selects the 4 points that approximately spans the largest area. This is important for collision detection. And if you look at this function, then you have a where operator, an argmax operator, and you have an absolute function which also could introduce a kink depending on how you implement it. And so what you can do now is just replace all of these functions with SoftJAX And the nice thing is, of course, now you can also play around with the different mode and types and see how your algorithm changes. If we do this, then this is the output of the algorithm of this function in the hard version. And what you see here is that the gradient is either 0.1 or 0. So some polygons are not taken into account because they don't form this largest area. And so the gradient is 0. So if you would try to optimize this, you wouldn't get well-behaved gradients. And then you have SoftJAX for tau getting close to 0 and SoftJAX for tau equals 1. So if tau goes to 0, then we implement it in a way that it approximates the hard function. And if it gets larger, then the function gets smoother. And what you see is that it's actually pretty close to the function. Of course, here the gradients are huge, which makes sense because this is a huge step function. So you also get steep gradients. So of course, SoftJAX doesn't solve this problem there. If you want to use this, these gradients, you would, for example, need gradient clipping. And just as a small example, if you have here this algorithm and this is the output, the points that the soft version selects, if you now slowly move the softness parameter to 0, then actually you go to the like all points collapse into a single point because it's a equal weighted computation of expectation for all these argmax operators. And in the end, you all select the same point. Yeah, that's it. First of all, I want to thank my colleagues, Anselm Paulus, which made major contributions to this framework. And of course, Georg Martius, which is our supervisor and our group lead and an amazing PI. Viet Musil, Sebastian Hoffmann, and Onno Becker, who also all helped us making this framework become a reality. If you're interested in contributing to SoftJAX or using it, or SoftTorch, here is the paper, the name of the archive paper. Yeah, and that's it. Thank you very much.